All right, so this presentation is called Loads and Power, but it's really about what I just said, those measurements. So it's just a scenario, we're not actually going to do this, but it says, hey, you're discussing with a school administrator about priority loads and a potential blackout. They say they want a light in every classroom, hallway, and bathroom, access to power in the nurse's office, and power to a central computer. Is this feasible? It's a great question. What we're going to talk about today is all the things that would let us figure that problem out. I think we're going to figure out problems like this a different day. But today, we're going to learn these terms down below. So the question: how do we know what our solar suitcase can power? To answer this, we have to be able to describe and measure all kinds of things. And so we're going to learn about amps, which is electrical current, volts, which is voltage, power, which is watts, and amp hours, which is how much of a charge, like stored energy, you have in a battery. We don't have the solar suitcases with us because we're not in person. That's okay. All right, so the first term is current. Current is the rate at which electrons move through a circuit, and it's measured in amps. So it says on here in the graphic that it's measuring the number of moving electrons. Now, it's not literally like if it was literally the number of electrons, the number might be in the millions or billions, but they have a way of measuring it, and it's called amps, and you have these special meters that you use. So if we imagine an electric circuit like a spinning water wheel, that image over on the right, the amps would be like talking about the gallons per minute, how much water is moving through the pipe. Not how hard the water is pushing, but how much water is actually moving through. So let's go back here. Here's two images. They show the same waterfall at different times a year. So I'm asking you, which of these shows greater current? Just that. Yeah. Thank you, Scott. And Caleb and Fiona, you're all correct. So it's the one on the left. If this was, it seems like a slightly different angle of the photograph, but anyway, I believe it is the same waterfall. It looks like it's up in Yosemite. It's a beautiful waterfall, but the one on the left has a lot more water going over the falls, right? So the water's falling the same distance, but one of them has a lot more water than the other. That shows more current. So current can only be measured when a circuit is complete and the electricity is moving. You can't measure current in a circuit that's turned off. And just for reference, the light bulbs that come with a solar suitcase they use about 0.4 amps. Next, we're going to talk about voltage. Voltage is the pressure, the electrical pressure moving electrons through the circuit. So they got a little picture of a fist, and then they're saying over in the image on the right, pressure is, in this case, would be caused by how much water is up in the tank pushing down on the exit pipe. But you could imagine, you could have a hose that's putting just a little dribble of water out, or that's pushing the water really far, in fact, you could put your thumb over the end of a hose and make the water spray really far. That simulates like increasing the voltage of water in a system.
Is it possible to have low voltage but high current?
Yeah, so you could have maybe imagine that the pipe is really very big, and so you could have a lot of water coming through it, but it's not pushing very hard. Yeah. Yeah. As opposed to like a fire hose. So let's look. Here's two different waterfalls. Which one do you think represents higher voltage and why? Go ahead and answer on the chat. Somebody besides Scott, Caleb, or Fiona.
A, maybe just because it's falling at a higher rate.
Yeah, good statement. That's what I would say. A, because the water's falling farther. You know, another way to think about voltage is if you took a ball or let's say a rock. If you drop a rock from 1 inch off the ground, you know, it hits the ground with a certain pressure. If you take that same rock and drop it from 5 feet up, it's going to hit the ground a lot harder. That's a great way to think about voltage. That'd be higher voltage, you know, in the end when the rock hit, as opposed to hitting from a very short fall. Voltage. Yeah, good point, Jacob. Voltage produced by a battery or a solar panel is best measured when the circuit isn't complete. So you could just measure the voltage on a battery without the rest of the circuit. You have a thing called a voltmeter or a multimeter that you connect a little wire to each side and measure it. All right, so battery voltage is an important part of a solar circuit or any circuit. The solar suitcase that we're working with, they use a 12-volt direct current system, DC system. So, and they come with this 12-volt light bulb that can just be plugged directly in. They also come with a little 5-volt converter that lets you charge like a telephone, because telephones want 5 volts on a USB circuit, not 12 volts. But it's the same thing. If it looks like what you might put into a car, it's exactly the same thing. And then there's these things called inverters. There's a picture of one on the screen on the right, on the bottom. An inverter takes direct current and turns it into house current, 120-volt standard current. And you could plug one of those into our solar suitcase. The trick is you can't then run a refrigerator or something big. It could only run something small like a light or something low power, maybe a computer, but not not a hair dryer. All right, now here we've got a little film of these girls. I wish I could hear them singing what they're singing, but power is the capacity of an electric system to do work, and it's measured in watts. So in our water tank image over to the right, power is the wheel actually turning as the water goes through. So it's actually a very simple equation. Power equals current times voltage, or we could say watts equals volts times amps. I'm wondering if, yeah, right here, I give you the formula. So let's do a little math problem. I told you earlier the light bulb used 0.4 amps and that the system is a 12-volt DC system. So let's use that to calculate how many watts the light bulb is. And you just plug it into the formula. Watts equals volts times amps, or amps times volts. So we know it was 0.4 amps and 12 volts. And when we multiply those together, we get 4.8 watts. So, for most purposes, you could round that up to 5 and say, okay, it's a 5-watt light bulb. You're all probably somewhat familiar with watts when you talk about light bulbs. I mean, I would imagine you are. You when you have a burnout light bulb, you unscrew it, and then you can look on the base of the light bulb, and it says how many watts it is. That's what we're talking about, and the power or the work that happens with a light bulb is heat and light that comes into the room, and but everything that uses electricity has a watt measurement. Like a toaster might be 1,500 watts, 1,500 watts. A hairdryer could be even more than that. So we're going to do another little formula. So we have a 60-watt light bulb at home plugged into a 120-volt wall outlet. I want to know how many amps this bulb is using. So watch what we do here. I plug in 60 watts. So the 60 goes on the watt side of the equation. And then current, is amps. I just wrote amps instead of A, so you could see what we were talking about. And then the volts is 120. So I'm counting on you all to have enough math in you to know that you divide both sides by 120 here, and then you get amps equals 60 divided by 120, which is just a half. So a 60-watt light bulb, an incandescent bulb, like old, not a LED bulb, running on house current, uses a half an amp of power. I mean, that's real. That's not, I didn't just make this up. That's how you figure these things out. So today on your, today what we're going to do at the end of classes, I mean, at the end of this notes is, I've got a Google form and it's got a couple of these problems in there for you to do. And I'm asking, anyway, so you'll remember, just plug in the parts that we know and then do a little math to find the part we don't know, and you'll be fine. I would recommend doing that work on a piece of paper. So we've talked about amps, volts, and watts. And now we're going to talk about the last thing, which is charge, the electrical charge in a battery. And that's measured in amp hours. It's in this analogy of the water wheel, it's equivalent to how many gallons are in the tank, right? Or more. Yeah, if you think about if it's just the gallons of water in the tank, you run the water wheel for a while, there's less water in the tank, right? That the amp hours are going to go down when you use the power. So it's actually exactly this is the easiest of our measurements. Amp hours is the number of amps times the number of hours. I mean, it's literally just amps times hours. So 1 amp hour is the amount of charge needed to provide 1 amp of current for 1 hour. So they ask us a simple questionnaire. How many amp hours of charge would you need to provide 1 amp for 3 hours? 1 times 3.
3.
Yeah, exactly. It's 3. So it's just a very simple formula. Amps times time equals charge. But we're doing it in amps and hours when we're not minutes. But so here's another interesting problem. The battery that comes with a solar suitcase stores up to 10 amp hours of charge. So managing the charge of the battery is an important part in an emergency. They say, hey, imagine it's 11 in the morning and your school experienced a blackout. You want to use your solar suitcase to keep the classroom lit because you're prepared. The battery's fully charged. You power a 0.4 amp light bulb until 3:30. So for 4.5 hours. How much charge will be left in the battery? So we started with 10 amp hours. And so we want to do 0.4 times 4.5. That's how much power we will have used. So remember, current times time equals charge. So we're going to do 0.4 times 4.5 hours. So that means that light will have used 1.8 amp hours. And then we can just subtract that from 10 where we started, right? 10 minus 1.8 would be 8.2 amp hours left in the battery. So I don't think I give you one this complicated in today's, Google form. But we'll, this is something we'll continue to talk about. So the solar panel that comes with the solar suitcase looks like that, and it can produce 2.8 amps of current when it's in full sunlight. So let's just take a different scenario. Let's imagine our 10 amp hour battery, that AH stands for amp hours, has been used up halfway. So we've used half of the power. It's only got 5 amp hours left. How many hours of charging, solar charging, would it take to fully recharge the battery if we're getting 2.8 amps of current out of the panel? Well, we can do the formula. So current times time equals charge. So down below, you can see, we know we need 5 amp hours of charge, right? Because we were at 5, we need 5 more for the battery to be fully charged. And we're getting 2.8 amps of current when it's in full sun. So it's kind of like saying 2.8 times X equals 5. So we would divide both sides by 2.8, and then we would get I guess I brought that up so I could show you. Then we'd get the number of hours. We're dividing both sides by 2.8, and 5 divided by 2.8 is 1.8. So it'd take just under 2 hours to charge up the battery if we had that scenario that we have here. Any questions? I wrap it up right here with a little summary. So let's review everything we learned today. Current is the measures the amount of moving electrons. Volts measures electrical pressure. Watts measures electrical power. Amp hours measures electrical energy stored in a battery, which we also call the charge. And then we have two formulas. Watts equals volts times amps, and amp hours equals amps times hours, or current times time. I feel like I wonder, kind of want to just add another line here. Charge equals current times time. That is a helpful way to be thinking about it. I know the little slide controller's in the way, but there you go. So those are that's what we covered today. I think this is, oh yeah, that was my second to the last slide. Here's the last slide. So your assignment today is to complete this Google form practice. It's got 10 questions in it. I'm going to post it on the assignment. Here's the deal. You can do the form as many times as you want. To get full credit, I need you to get 8 out of 10 or better. And so, do your best, and then it'll tell you what your score was. And if you got 6 out of 10, read what it says. I explain on most of the answers. I give you help. I say why the right answer was the right answer. I give you some tips, and then you can try again. It's a pretty short thing, and you might even remember, oh yeah, it was B, not A. But one way or another, after midnight tonight, I'm gonna look and see if you got 8 out of 10 or better on one of your runs. I'll take your best score is what I'm trying to say. But you can do it as many times as you want. If you get 8 out of 10, 9 out of 10, or 10 out of 10, I'll give you full credit for the day. Otherwise, I'll just be giving you partial credit. But because I want you to, if you don't get it all right, I'd like you to try again. All right, I'm gonna